Okay, you remember a while ago I actually spoke to you about circuits which were called comparators. Okay, so let's just quickly recap. So if we take an operational amplifier, this is going to be in the open loop mode. So this is my non-inverting inverting input. Let me show you the power supplies. So let's say this guy is set to plus 15. This guy over here is at minus 15. This is my output voltage sitting here. Let's call this input V in, and let's hold the voltage at the inverting input to 2 volts. All right. Now let's look at what happens when we actually change V in. So we're going to make a couple of statements. If V in, let's say, is less than 2 volts, what happens to the output? Well, the output's going to go into a saturated value. So that means that this voltage here is 2 volts. This is a little less than 2 volts. So the voltage at the inverting input now is bigger than the voltage at the non-inverting input. The output becomes a minus 15. It hits that saturated value. If V in is, let's say, greater than 2 volts, that means that this voltage here now is bigger than the voltage at the inverting input. Then the output over here goes to a plus 15, which is a saturated value. So what we could say here is that really we're looking at V in and we're comparing V in to a value of 2 volts. So if V in is bigger than 2 volts, the output is plus 15. If V in is less than 2 volts, the output is a minus 15. All right, let's have a look at an example here of how we might use a comparator. So here we have our op-amp comparator. The inverting input is set at 6 volts. All right, now this is a system that could be used in a car to actually cool down the radiator. So what you have is a motor here and there's a fan attached to that motor. And it's that fan that's going to cool the radiator. You have a motor drive circuit over here which is used to turn on basically that motor. All right, now let's have a look at what's happening here. Let's supposing this input voltage V in is less than 6 volts. The output over here is going to be sitting at what? Yes, a minus 15. If this is sitting at a minus 15, then basically this motor drive circuit is not turning on the motor over here. So the fan is not turning. As the temperature increases here, V in increases. So we've got a transducer here that basically gives me a voltage that's proportional to temperature. So the temperature goes up, V in goes up. We're going to reach a point, are we not, where V in becomes 6 volts plus just a little bit. What does that mean? It means that this voltage over here is going to switch from a minus 15 to a plus 15. That's the input to the motor drive circuit, which is going to cause the actual motor over here to turn on. The fan now starts to turn, spin, and causes the radiator to cool. All right. Is that a workable system? Well, you might say, yes, it is a workable system. And it's certainly a system that works okay, providing the car is really not stuck in traffic. Let's supposing the car is really stuck in traffic. What's going to happen? Let's consider that. The car's not moving, but the engine is running. All right. So the engine's running, which means that the radiator is going to get hotter. Okay, as the radiator gets hotter, this voltage builds up. It reaches again that 6 volts plus a little bit. Okay, what does that do? Causes this output to become a plus 15. That causes the motor to actually turn on, turning the fan on. Then what happens? This radiator starts to cool. This voltage drops. This drops to a voltage just a little bit less than 6 volts. Okay, what happens over here? This voltage switches back to a minus 15, basically turning off the motor over here. What happens next? Well, the fan is now off. The radiator starts to heat again, okay, which means that this voltage starts to creep up again. It reaches 6 volts plus a little bit. This switches back to a plus 15. Then what happens? The fan now turns on again. And I think you could see if we're actually standing in traffic, so the car is not moving, we're actually standing in traffic, then basically this fan is going to turn on, turn off, turn on, turn off, turn on, turn off, which is really not a desirable situation. So we really want a better system than this, really. So we need to think about maybe, yes, this is simple, but we might need to add a degree of complexity that we have a turn-on voltage, let's say that is 6 volts, but we have a turn-off voltage which is less than 6 volts, maybe 4 volts or something of that sort. So we need to think about how we might design a circuit to actually do that. Okay, let's have a look at this circuit that we have here. Now the first thing to really notice is that I've got a feedback connection from that output through this R2 resistor over here to where? To the non-inverting input, okay? This is a positive feedback connection, which means that this output over here is going to be sitting in a saturated condition, either plus 15 or minus 15, if those are the power supplies to this operational amplifier. All right, now let's just label this voltage at the node here, and we're going to say that's V1. All right, now let's think about this, okay? Supposing I adjust this V in such that this V1 over here, and I'll write this down, V1 is actually less than the reference voltage Vref, okay? What's the output over here going to be? Remember, this voltage at the node here is less than the reference voltage, which means that this guy here at the inverting input is bigger than the V1 voltage at the non-inverting input. Yes, that means that my output over here is going to be in a saturated value of minus 15 volts. All right, let's supposing I start to increase V in. So I start to increase V in. So I'll write that down. We're going to increase V in. Now I'm going to bring V in to a value such that this V1 voltage over here is equal now to the reference voltage. Let's say it's just a little bit bigger than the reference voltage, fractionally bigger than that reference voltage. What's going to happen? This guy now is fractionally bigger than the voltage at the inverting input, which means then that the output is now going to switch what? It's going to switch to really a plus 15 volts. Okay, so I increase V in, let's say, until V1 is equal to the reference voltage plus just a little bit more, then that output voltage, V out, is going to switch to a plus 15 volts. So we could say then that switching occurs, right? Switching occurs when what? V1 is equal to that reference voltage, okay? Now the question is, how do I calculate, how do I find that V1 voltage? So how do I find V1, okay? Now let's think about this. This is something I'd like to you to really think about. We'll take a break here, so I just want to get the concept across. How do you think you would calculate that voltage? Well, V1 is made up of what? Well, we have to assume a condition for V out. So we could assume a starting condition for V out. V out could be sitting at what, a minus 15 volts. Okay, so this voltage here could be sitting at a minus 15 volts. Okay, so then what about this V1 term here? V1 is made up of this minus 15, isn't it? That's having an effect on it. And also whatever the input voltage is. So it's really a function of two voltages. V1 is a function of whatever V in is, and it's also a function of whatever this output voltage is, which is going to be in a saturated value. How do you think you might do that? Well, have a think about it, and a little hint here, maybe you could use, and there are other techniques to use, but maybe you could use superposition to actually find that V1 voltage.